Okay, so we are doing, by the way, check out my new mic. I should sound pretty good. All right, so we're going over differential equations, Blanchard, section 1.5, existence and uniqueness of solutions. So just remember, in the last section, the last few sections have been all about studying the three different ways of studying differential equations, which is qualitative, quantitative, or analytic, I guess, and numerical. Okay, so we have seen analytic, qualitative, and numerical techniques for studying solutions of differential equations. One problem we have not considered is, how do we know there are solutions? Although this may seem to be a subtle and abstract question, it is also a question of great importance. If solutions to the differential equation do not exist, then there's no use trying to find or approximate them. Here, let me zoom in. Okay. Um, More important, if a differential equation is supposed to model a physical system, but the solutions of the differential equation do not exist, then we should have serious doubts about the validity of the model. Right. To get an idea what is meant by the existence of solutions, consider the algebraic equation 2x to the fifth minus 10x plus 5 is equal to 0. A solution to this equation is a value of x for which the left-hand side is 0. In other words, in other words, it is a root of the fifth degree polynomial. We can easily compute that the value is minus 3 if x equals 1 and 13 if x equals minus 1. Since polynomials are continuous, right? Since polynomials are continuous, there must therefore be a value of x between 1 and minus 1 for which the left-hand side is 0. So we've established the existence of at least one solution of this equation between minus 1 and 1. We did not construct this value of x or approximate it, other than to say it's between minus 1 and 1. Unfortunately, there's no quadratic formula for finding roots of fifth degree polynomials, so there's no way to write down the exact values of the solution of this equation. But this does not make us any less sure about the existence of this solution. The point here is that we can discuss the existence of solutions without having to compute them. Okay. So yeah, so that's the main point of this whole page. Okay. So I'm going to write that down. All right. So it is possible that there is more than one solution. It is also possible there is more than one solution between minus 1 and 1. In other words, we may not have a unique solution. In the same way, if we are given an initial value problem, we can ask whether there is a solution. This is a different question than asking what the solution is or what the graph looks like. We can say there is a solution without having any knowledge of a formula for the solution. Just as we can say the algebraic equation above has a solution between minus 1 and 1 without knowing its exact value or approximate value. Okay, so now we get into the existence theorem. Now, I've read this a little bit, but I didn't really get it. The question of existence of solutions for differential equations has been extensively studied, and some very good results have been established. For our purposes, we will use the standard existence theorem. Suppose f of ty is a continuous function in a rectangle of the form ty, where t is less than b and greater than a, and c is less than y, which is less than d. If t0, y0 is a point in the rectangle, then there exists an epsilon greater than 0 and a function y of t defined on this open interval. T0 minus epsilon, T0 plus epsilon. That solves the initial value problem. Okay, this theorem says that as long as the function on the right-hand side of the differential equation is reasonable, solutions exist. It does not rule out the possibility that solutions exist even if, but it just doesn't guarantee it. When we are studying the solutions of a reasonable initial value problem, we are studying the solutions of a reasonable initial value problem. Or when we are. Okay. All right, so extendability. Let's see, what does that mean? Given an IVP, the existence theorem guarantees that there is a solution if you read the theorem very closely with a lawyer's eye for loopholes, you will see that the solution may have a very small domain of definition. The theorem says that there exists an epsilon greater than 0, that the solution has a domain that includes an open interval. The epsilon may be very, very small, so although the theorem guarantees that a solution exists, it may be defined only for a... Oh, that's no good. This damping thing doesn't really work. I gotta be careful not to hit this thing. It's probably really annoying. What if I just keep it away from me? Okay. All right. So, unfortunately, this is a serious but necessary condition. Consider the IVP one plus y squared. Okay. The slopes in the slope field for this equation increase in steepness very rapidly as y increases. Hence, dy dt increases more and more rapidly as y of t increases. There's a danger that solutions blow up, tend to infinity very quickly as t increases. By looking at solutions sketched by the slope field, we can't really tell if the solutions blow up in finite time or if they stay finite for all time, so we try analytic methods. This is autonomous, so we can separate and integrate. Okay, then we get this, and then we get, okay, tan, which is the general solution of the differential equation. The IVP, okay, so then we get tan C. So C is equal to 0 or n pi. Thus, the particular solution is y of t is equal to tan t. And the domain of definition, that's kind of an interesting point. As we see from this picture, the graph of this particular solution is vertical asymptotes at pi over 2 and minus pi over 2. As t approaches pi over 2 from the left and minus pi over 2 from the right, the solution blows up. If this differential equation or a model of a physical system, we would expect the system to break as t approaches pi over 2. All right, so this is a slope field, and this is the particular solution. Okay. Solutions that blow up or down in finite time is a common phenomenon. Many relatively simple looking differential equations have solutions that tend to infinity in finite time. I'm actually surprised because really, if you had asked me, do you think this thing blows up? I would have said no. I would say no. Okay, but it does. So, anyways, all right. Many relatively simple looking differential equations have solutions that tend to infinity in finite time. When dealing with IVPs of the form, we have always said, consider the solution. By the existence theorem, we know there is a solution, but how do we know there is only one? Why don't we have to say consider a solution instead of consider the solution? In other words, how do we know that the solution is unique? Knowing that the solution to an IVP problem or IVP is unique is very valuable both theoretically and practically. If solutions weren't unique, then we would have to worry about all possible solutions, even when were doing numerical or qualitative work. Different solutions could give completely different predictions for how the system would work. Fortunately, there's a very good theorem that guarantees the solutions of IVPs are unique. All right, suppose f of t and y, and the partial of f with respect to y is a continuous. So, okay, is continuous. In the domain if t0, y0 is a point in this rectangle and y of t and we have two functions that solve the initial value problem. For all t for some epsilon. Then we know that these two solutions are actually equal. Before giving applications of the uniqueness theorem, we should emphasize that both the existence and uniqueness theorem have hypotheses, conditions that must hold before we can use these theorems. So I don't think they go into the proofs in this book, unfortunately, but before we say that the solution of an IVP exists and is unique, we must check that f of ty satisfies the necessary hypotheses. Often we lump these two theorems together using the more restrictive hypothesis. Right, because, okay, so let's just write this down. So the existence theorem then Okay. So uniqueness, however, requires the stronger condition that also the partial of f with respect to y is continuous too. So I would like to look at an example that's has a solution that exists, but it's not unique. Okay. It is pretty okay, so lack of uniqueness. It is pretty difficult to construct an example of a sensible differential equation that does not have solutions. However, it is not so hard to find examples where y of t is a decent function, but where uniqueness fails. Of course, these examples, either f of ty is, well, I'm sorry, I keep bumping it. I should have it like a boom. I should have it hanging above me or something. I don't know. Test, test, test. Okay. I don't know. Maybe it sounds good, maybe it doesn't. I just have to be careful. Okay, so, or partial f, partial y is not continuous. Consider the differential equation dy dt is equal to 3y to the 2/3. The right-hand side is a continuous function on the entire ty plane. Unfortunately, the partial derivative of y to the 2/3 with respect to y fails to exist if y equals 0. So the uniqueness theorem, but I thought it just had to be on. Okay. So the uniqueness theorem does not tell us anything about the number of solutions to an IVP of the form y of t0 equals 0. Let's apply the qualitative and analytic techniques that we've already discussed. If we look at equilibrium solutions, we see y of t equal to 0 for all t is a solution. Second, we note that this equation is separable, so we separate and integrate. I'm just integrating it. Okay, so then you multiply by 3, and then you cube it. So y is equal to, and this is going to be 3t. Wait, did I do this wrong? Wait, how could I have possibly done this wrong? 3. Oh, wait. Oh, because you divide. Oh, you divide. That's why. Okay, because I multiply by 1/3. So yeah, you're gonna get 3y. So then you divide. Okay, so then you do get y of t is equal to t plus c cubed. Okay, great. Now consider the IVP. Oh, interesting. Wait, what? Okay, let's just read it. That's gonna be so annoying. I don't remember that being a problem earlier. The smallest bump is so loud. All right. Now consider the IVP. Y of 0 is equal to 0. One solution is y of t is equal to 0 for all t. However, a second condition is obtained by setting c equal to 0 after we separate variables. Then we have y2 of t is equal to t cubed. Consequently, we have two solutions to the same IVP. The slope field and the graphs of the slope field and the graphs of the two solutions and the graphs of two solutions. The uniqueness theorem says that two solutions to the same initial value problem are identical. The result is reassuring, but it might not sound useful in any practical sense. Here we discuss a few examples to illustrate why this theorem is in fact very useful. Okay, so we have two solutions to a differential equation, and it's continuous, and its derivative with respect to y is continuous. If for some t0 we have y1 of t0 is equal to y2 of t0, then both of these functions are solutions of the same initial value problem. The uniqueness theorem guarantees that y1 of t is equal to y2 of t, at least for all t for which both solutions are defined. We can paraphrase the uniqueness theorem as, if two solutions are ever in the same place at the same time, then they are the same function. Bro, I'm not integrating that. That's crazy. On the other hand, if y is equal to 2, we have an equilibrium. Suppose y2 of t is the solution to the differential equation that satisfies the IVP. The uniqueness theorem implies that y2 of t is less than 2 for all t, since the graph of y2 of t cannot touch the line y equals 2, which is the graph of the constant solution for this first solution. Okay, yeah, so they never touch. This observation is not a lot of information about the solution of the IVP. On the other hand, we didn't have to do a lot of work to get this information. Identifying the equilibrium solution is pretty easy, and the rest follows from the uniqueness theorem. By doing a little bit of work, we get some information. If all we care about is how large the solution of the original IVP can possibly become, then the fact that it is bounded above by y equals 2 may suffice. If we need more detailed information, we must look more carefully at it. We can also use this technique to obtain information about solutions by comparing them to known solutions. Consider the differential equation 1 plus t squared divided by 1 plus y squared. It is easy to check that y1 of t equal to t is a solution. Wait, what? I don't get this. Hold on. Oh wait, we needed I need to practice that more because I always trip that up on verifying solutions. Oh yeah, okay. So if we have y1 of t is equal to t, then dy dt is equal to 1 for, and we know that y on the right-hand side is t, so we can substitute that. So we have 1 plus t squared over 1 plus t squared, and we can see that that does equal the left-hand side, which is just t. Or, sorry, which is 1. So 1 equals 1. So we're good there. All right, so it's easy to check that that is a solution. And if, yeah, the initial value. If y2 of t is the solution satisfying the initial condition, y0 is equal to minus 0.1, then y2 of 0 is less than y1 of 0. So for all t, it's going to be less than it. Okay, yeah. So if we're given y1 of t equal to t is a solution, and it's easy to check, then if given another solution, we have a bound. But we also need to check that this with respect to y is continuous at 0. Which I don't know if it is. Oh, and then they actually did the substitution, so okay, that's cool. Okay, in some cases we can use the uniqueness theorem to and some qualitative information to give more exact information about solutions. Consider dy dt is equal to y minus 2 y plus 1. Okay, so we have equilibrium solutions 2 and -1. By the existence and uniqueness theorem, any solution y of t with an initial condition oh right, yeah. So that's another one. So if we have have two solutions, equilibrium solutions, or actually, I think this applies more generally to any two solutions. I think, yeah, it applies to any two. If you have two solutions to an IVP, then your solutions, and it's unique, you've verified that the solutions are unique, then you're going to have to stay within those bounds for any other solution that has a point in there. In this case, we can say even more about this. Consider the solution to the IVP y of 0 is equal to 1/2. Not only do we know that -1 is less than y of t is less than 2 for all t, but because this equation is autonomous, the sign of dy dt depends only on the value of y. Wait. How do we know that f of y is less than 0? Oh, just because it's not a general thing. It's just be this specific differential equation. Hence, the solution satisfies less than, consequently, the solution is decreasing. Since the solution is decreasing for all t, and since it always remains above -1, we might guess that y goes to -1, and this is exactly what happens. If y of t were to limit to any value y0 larger than -1, then when t is very large, y of t must be close to y0. What? But f of y0 is negative. So when y of t is close to 0, we have dy dt is close to f of y0, which is negative. So the solution must continue to decrease past y0. That is, solutions of this differential equation can be asymptotic only to equilibrium solutions. Okay, great. Yeah. That's super, super cool. I actually really, really like that. As with all right, so uniqueness and numerical approximation. As the preceding examples show, the uniqueness theorem gives us qualitative information concerning the behavior of solutions. We can use this information to check the behavior of numerical approximations to solutions. If numerical approximations violate the uniqueness theorem, we are certain something is wrong. The graph of the Euler approximation of the solution e to the t sine y okay. Oh yeah, so we can easily check that we have a constant function solution. So because So because the numerical solution said that it's not trapped, but it is trapped, then there's something suspicious going on here. This equation is unusual because the e to the t term on the right-hand side, when t is large, the slopes become really big. And so Euler overshoots. All right, so let's do some of these exercises. All right. Exercises. We refer to a function f, but we do not provide its formula. However, we do assume that f satisfies the uniqueness theorem hypothesis for the whole ty plane. We do provide various solutions of the given differential equation. Finally, we specify an initial condition. Using the uniqueness theorems, what can you conclude about the solution of the to the equation with the given initial condition? What's up, Riley, bro? It's been forever, man. It's been forever. I'm just doing schoolwork, bro. I'm just doing schoolwork. It's been forever, man. Check out my new microphone. I got a new microphone because the other one broke. All right, so if y1 of t equal to 3 for all t is solution, and y of 0 is equal to 1. It did? Hey, does this one sound good? Is this one actually sound good now? Oh, that's very nice. That's super good to hear. It was only $50, but then I had to buy this stand, so it was like $70. But I'm so glad that it's better because I've always been self-conscious about the audio. But now I can talk real close into the mic like this. Get real, Anyways, so let's just figure this out. So we have this differential equation, and we know that it's continuous, and partial of f with respect to y is also continuous. We have an equilibrium solution at 3. I mean, I think that this is going to be easy. I think the thing we can conclude is that for the solution like y2 of t where y of 0 is equal to 1, we know y2 of t is bounded above by 3 for all t. So I think that that's what you're supposed to write. Okay, so now let's do the second problem. All right, so this, let's see, does it ask us to graph the solution? No, because we don't really have any. So number two is, okay, so this is interesting because we have an autonomous system. All right, so let me write that down. So y dot equals f of y. So first off, autonomous. The second thing is we have 3 equilibrium solutions. We have y1 equal to 4, y2 equal to 2, and y0 equal to, or y3 equal to 0. Tiny CNC is kind of on hold just because I have a ton of classwork. But I also just got pretty tired of it. I started doing started reading this really cool book, and I just got totally focused on that. I mean, this book is like trippy as hell, man. This book is so good. Introduction to the Theory of Computation. I wish I had read this book in college. But so anyways, I got distracted. I was like tired of doing applied stuff, and I wanted to switch back to doing something, you know, theoretical, where you just think about it and you're just like, wow, we can really prove this. All right, so we have y of 0 is equal to 1. All right, so we know that y of t is going to be in, or whatever, the range 0 to 2 for all t. But I don't know if we know anything else about this. I feel like the fact that it's autonomous means that maybe we know something even more. All right, we'll jump back to that one. I mean, I want to check my answers on a lot of these because I got a quiz coming up. Okay. All right, now we're given two solutions. Dude, chemistry? Oh, bro, that's so cool. I'm about to do a bunch of chemistry over the summer. I'm taking two quarters worth of chemistry. Dude, I have so much chemistry coming up. But yeah, I love chemistry. Chemistry was my favorite class in high school. I took AP Chem, and now I got to do a bunch of college chem, and then I got to do organic chemistry, and then I'll be done with my chemistry requirement. But yeah, I love chemistry. Chemistry is so cool. Okay, so we have y dot equals f of ty, so it's not autonomous. And then we have y1 of t is equal to t plus 2, and then y2 of t is equal to minus t squared. So if we were to plot this, dude, I actually like Desmos. I was like hating on Desmos because it's what I use in high school, but it's not so bad. So if we were to like, oh, actually, I don't want to do that. So what are the two equations? So we have minus t squared. Oh. And we have x plus 2. Okay, so these solutions never interact. But what's great about this is, and then the initial condition of y of 0 is equal to 1. So we know that it's just bounded by them. I don't know if we know anything else. Let me actually get my phone out because I don't know, my Twitch chat or my chat was breaking the other day. Okay. All right. Number 4. Y1. So first off, not autonomous, not auto. Then we have y1 of t is equal to minus 1 for all t. And then we have y2 of t is equal to 1 plus t squared. And then we have y of 0 is equal to 0. You broke the laptop? Do you have another computer? I mean, damn. Dude, it's a... Oh, really? That sucks, man. But you got a new one or you repaired it? Oh, cool. Okay, so let's plot these again. Actually, here's what I'm going to do. Let's do this. And minus 1, and then 1 plus t squared. Ah, squared. Okay, so, oh wait. Can we do this? Oh wait, no, this is going to be y is equal to minus 1. Just replace, yeah. Well, that's cool. I mean, it sucks that you broke it, but now you're back on the internet, man. And that's where all the cool kids hang out. Okay, so we have... All right, so I think this is just more of the same, right? Let's do a double check on this one. I just want to know what... Let's just do like a little double check. Chicken jockey? What? Okay, so let's see. There's exactly one solution. Okay, oh yeah. So okay, that's really what I should be saying is that we have okay, we have a unique solution. For all of these, we have a unique solution for all of these. Okay, great. So it's not, there was nothing else. There was nothing else that you needed to say. It was just checking that, okay, this solution is going to be bounded in there. All right. Now we're going to be studying a specific solution. Let's get a look at this thing. You've been on Twitch? Dude, you left me, man. That's messed up. Nah, I don't care. I also stopped streaming for a while too. Because I was just reading a book and it was like kind of boring. Alright, so let's turn these guys off. Alright. Trolling a streamer playing Beat Saber. What does the existence uniqueness... Okay. Alright, so let's do this one. So we have 5. So first off, we have dy dt is equal to y times y minus 1 times y minus 3. You made songs, dude? You make music? That's super cool. I used to make a lot of music. Alright, so we have 0, 1, and 3. And we know the sign is positive. So okay, and we know that this is the reason why we know it's continuous is because if we take f of y df of y dt del t or del y is a polynomial. Oh, so you're like who's that guy, dude? Yeah. There's a lot of people that do this intentionally. All right. So because the partial derivative of f of y is a continuous, is a polynomial, then we know that it's continuous, and this is continuous, and its derivative with respect to y is continuous. So that means that this is solution exists through it, and is unique. And it should be for all t. I don't know if we can claim that for epsilon. The grind is real, absolutely. And then the other thing that we know is that since dy dt is greater than 0 for y of 0 for wait, hold on. Hold on. So if we have y squared minus y times y minus 3, we're going to get y cubed minus 3y squared minus y squared plus 3y. So y cubed minus 4y squared plus 3y. If we integrate this whole thing, we're going to get... Oh, wait, but we have to integrate the 1 over it. So it's going to be like the integral of 1 over y cubed plus the integral of... or minus 4 times the integral of 1 over y squared plus 3 times the integral of 1 over y. All right, so let's try... I am curious what the solution to this is. So I'm guessing it's going to be like minus 2 to the y minus 2 minus 4 times this is going to be there's going to be plus 4 y to the minus 1 plus 3 ln y. That's what I think it's going to be. Okay, so I have my answer, and that's going to be equal to t. That's going to be equal to t. Oh, wow, wait, you don't have to do partial fractions for that, I think. I think you just use the power, right? Oh, no, you know why you can't? Yeah, I'm actually mistaken. You definitely can't. Yeah, so I'm wrong. Yeah, you definitely can't. All right, so this is actually... Okay, so then what am I trying to say? That if the derivative... So if... Hold on. No, yeah. Okay, so at t0, y is 4. So if we plug in 4 to this, we are going to get a positive times a positive times a positive. And so the whole thing is positive. So that means that it's going to asymptotic to infinity. So it's going to just keep going up. All right, number 6. All right, for the solution 0, we know it's constant. So it's constant. It's unique. What else? I don't know what else you could possibly say. I mean, it's a constant unique solution. Number 7 equal to 2. It's bounded by 1 and 3, but approaches 3. So it approaches y of t is equal to 3, but it doesn't actually get there. And then minus 1, if we plug in minus 1, we're going to get a minus times a minus times a minus, which is a minus. So that means so for 7, oh, that's 7. For 8, it goes to minus infinity. All right. Number 9. Let's see how many are on this one, because we need to do 1.6 and we need to do 1.7 today and tomorrow, and then I have so much homework. Okay, show that these two are solutions to this. Okay, so I got that. That's pretty easy. All right, so the first thing we do for 9 is we're going to just try the first one. So y1 of t is equal to t squared. So then dy dt is going to be equal to 2t. So what we're going to have on the left-hand side is 2t. And that's going to be equal to, and now here we substitute in the actual solution. So we're going to get minus t squared plus t squared plus 2 times t squared times t squared plus 2t minus t squared minus t to the 4th. So this is just going to be minus t to the 4th plus t squared plus 2t to the 4th. So this cancels, and minus t to the 4th cancels. Plus 2t minus t squared. So the t squareds cancel, and you get 2t is equal to 2t. So there we go. We've checked that that is indeed a solution. Now the next one's going to be even more annoying. I wonder if we can just use a program. Honestly, you know what? Just for fun. You know, I never have fun anymore. That's not true, but I want to have some fun. Let's see. Can I do this? I thought I added it to my path, but I guess I didn't. We need to go. Wait. Wait. It's not called Rust, is it? It's called duck cargo. I forgot how to do this. All right, so let's just see if this works. I'm like so curious. Okay, so what we're trying to do, set x, and this is going to be, this is ridiculous, man. This is going to be, okay, wait, let me write it out. So it's minus y squared plus y plus 2y t squared plus 2t minus t squared minus t to the fourth. All right, let's just see if we can write this out. I don't think this is going to simplify out just because um, actually I think I can just do this. Is it plus? I think it's plus. So this is going to be plus y times 2y pt plus times 2t. Oh, wait. So we got the 2t, now we got times minus 1 tt times minus 1 power t4. Okay. Now we're going to do replace all x rule y, and then y is going to go to what? Plus power t2 1. So the substitutions worked, but it did not simplify anything at all, which is annoying. Whatever. Okay, well, let's just do it by hand then. Yeah. I don't know why I thought I was gonna do that. I don't really want to dig into it right now, but it would have been really cool if it did simplify it. Okay, so we're gonna get, so we still want 2t on the left-hand side, and then we want do we really want to do this? This is gonna be so annoying. Okay, fine, let's just do it term by term. minus y squared is equal to minus times minus t squared plus 1 squared is equal to t to the fourth plus 2t squared plus 1. So this is a minus times all of that. Then we have y, which becomes t squared plus 1. Then we have 2yt squared is equal to 2 times t squared plus 1 times t squared is equal to 2t squared plus 2 times t squared is equal to 2t to the fourth plus 2t cubed. Honestly, do we want to do all this verification? I trust that it's a solution. How important is it that we actually verify that that's a solution? All right, show that if y of t is a solution to the differential equation in part A, and if um y of 0 is in between 0 and 1, then this is true. That's bounded. So, so the main things that we need to show is, first off, this is a polynomial, so it's continuous. And then what we want to show is also that this, with respect to y, is also continuous. So what we're going to do is we're going to just take this expression and do partial f, partial y. And so we're going to get minus 2y plus 1 plus 2t squared. And that's the whole thing. I'm pretty sure that's the whole thing. Yeah, I'm going to do this really quickly. I don't really want to do this. I wish I had well, whatever. We can just ask ChatGPT. Um. All right, great. I did it right. I should hope that so since this is a polynomial, it's continuous. Therefore, solutions to the the DE, and let's remember the actual statement of this whole thing. Okay. All right. So we just showed it because so then, immediately we apply uniqueness in existence to show solutions with y of 0 in 0 to 1 open are bounded by t squared and t squared plus 1. Cool. All right, this one's interesting, it looks like, because we have some weird absolute value nonsense in here. Okay. Show that the function y, show that we have an equilibrium at 0. So 0 is a fixed point because the square root of 0 is 0. All right, so 10a square root of 0 equals 0. So 2 times 0 is equal to 0. All right, so we're done with that. Now, B, find all solutions. The square root of a positive number can be negative. So, hold on. Hold on. All right, so B, find all solutions. Actually, does this thing have a mute button? That would be really nice. No, I'm just gonna mute it on here. All right, I'll be back in a second. Okay. All right. All right. So this one is actually really interesting. Let's see. How many are there in this thing? 18. Okay. I did 17 in class, but I want to go over it a little bit more. All right. Oh man. Okay, so let's focus up. I think the point is that it's symmetric. So first off, to show existence, we need to say that this is a continuous function. I wanna know how this shows up. Oh, that works. That works perfectly. Well, it's autonomous. Okay, actually, maybe we'll do this. So we're gonna get dy over. Oh, we're gonna get absolute value of y to the 1/2 dy is equal to 2 dt. So we're gonna get I don't know how to integrate this. Um, Oh yeah, because it's negative 1/2. Wait, is it negative 1/2? Oh yeah, it is, right. So it's gonna be square root, it's gonna be dy over square root of y. Okay, let me try integrating again. So we get y to the minus 1/2 is equal, dy is equal to 2 dt. And then we integrate and we get, so you add 1 and you divide by that. So you get 2 square root y is equal to 2t plus c. And you divide by 2 and you get square root of y is equal to t plus c. Then you square both sides, right? You get y is equal to t plus c squared. Wait, where am I? Okay. Okay, great. That's what I have. Um, and this is going to be plus or minus. Oh, interesting. Oh, that's really interesting. Okay. Okay, great. All right, so let me read its solution again. Wait, I'm so confused. So if y is greater than 0, what? Finally, you can glue these to y is equal to 0 at any time t is equal to alpha. So, okay, hold on. Yeah, this is a good problem because I don't really understand it. I mean, we can just look at this. So, okay, let's say that y is at 4, like actually at 4. Then the change is going to be plus or minus 2 times 2. So we have plus or minus 4. Oh, yeah, man. This problem is a good one because why do they get rid of the freaking? I don't know why they get rid of the absolute value though. Yeah, it's really weird that you can stitch solutions of differential equations together like this. Okay. I want to review this one on Monday, I think. That one's really weird. All right, 11. dy dt is equal to y over t squared. Show y1 of t equals 0 is a solution. That's obvious. B, show that there are infinitely many other functions that satisfy the differential equation that agree with the solution. That agree when t is less than or equal to 0. Damn, dude, this got difficult for me. So, all right, let's just try to integrate. Let's just try to do some work, you know. So we're gonna get 1 over y is equal to dt or dy over dy over y is equal to dt over t squared. So we integrate and we get ln absolute value of y is equal to minus 1 over t. Then we exp and we get y is equal to plus c, I guess. E to the wait. Did I do the integration wrong? If t is equal to 0, the derivative is undefined. Oh yeah, that's still the case. Um, where did Desmos go? Right. That's okay. Wait, but it's not like that. It's like this. But the slope, yeah, because the slope is going to be negative, but the value is positive. No, and it actually goes like this. That's this is a weird function, man. Okay. Okay, so this function, okay, so wait, so f of t y equal to y over t squared is not continuous at t equal to 0. So we aren't even guaranteed existence around here. So if, in other words, if our rectangle includes that point, but I don't know why this is less than or equal to. If t is equal to 0, then it should not be defined. We shouldn't be able to get a solution at that. They never said anything about this gluing thing. Yes, the uniqueness theorem. So we have C. So as t goes to infinity, we're gonna e to the 0, which goes to 0. So then I don't understand. Let's see. Wait, what? Oh, there's almost definitely gonna be a problem like this on this quiz, man. Excuse me. Okay, okay. All right. Number 12. What can you say about solutions Okay. All right, I can do this one. This one's easy. All right, so first off, we're going to show that they're solutions. So we have this is equal to 1 over t minus 1, and y2 t is equal to 1 over t minus 2. And we have show that their solution is dy dt is equal to minus y squared. So, uh, so we're going to take the derivative of both solutions. So we have t minus 1. Okay. Okay, so I'm pretty sure that the derivative of this is equal to minus 1 over t minus 1 squared is equal to dy1 dt. All right, so we need to say that minus 1 over t minus 1 squared is equal to minus 1 over t minus 1 squared, which is true. Okay, now for t minus 2, it's the same thing. It's going to be minus 1 over t minus 2 squared is equal to minus 1 over t minus 2 squared. Yep. All right, so I just showed that we have those two solutions. But what do we need to do next is so now if y of 0 is in minus 1 to minus 1 half. So let's plug in the 0 to both of these. We're going to get 1 over minus 1 is equal to minus 1 for y1 of 0. y2 of 0 is equal to 1 over minus 2. So we have minus 1 and minus 1 half. So if it's in between these two, which is this is y1 of 0 and y2 of 0, then it's bounded. No, but actually, I wish they had like an example exercise like my linear algebra book. Like it didn't say anything about how to solve these problems of okay. Dude, I need so much practice. So bad at this. Yeah, okay, cool. All right, good. So times -2. Okay. All right, oh yeah, because of the square root, we need a plus or minus. Okay, so that's that solution. Now the domain. Okay, state the domain of the definition of the solution. 1 over 0 is undefined. Okay, so if we have need to get some water. Okay, so okay, I'm gonna copy this over. Yeah, I really don't get the plus minus. Wait, oh, that's actually crazy. Wait, Mm. I think it's ln y minus 1. Yeah. Oh wait, let's Oh, I got the wrong one. Oh, wait. Oh, wait. Damn, I'm so dumb. No, we do get Y's? Dude, what am I doing? I'm like so out of it right now. Okay, I did this wrong, and then I did this sort of right, and then I did hella wrong. Okay, let's just start with number 14 again. Okay, we have dy dt is equal to 1 over y minus 1 times t minus 2, right? And then we have y 0 is equal to 0 as our initial condition. So now we're going to just solve this for the general solution. So we're going to multiply both sides by y minus 1. So we're going to get y minus 1 times dy is equal to dt, and we're also multiplying by dt over t minus 2. Okay, now we're going to integrate both sides. And we can, because of the linearity of integration, we can get integral of y minus integral of 1, and they're both dy. And so we're going to get y squared over 2 minus y is equal to, and then we're going to integrate the other side. And if we say let t minus 2 equal to v, then dv dt is going to be equal to 1. So dv equals 1 dt. So now we can substitute in there. So we can say the integral of dv over v is equal to the integral of dt over t minus 2. So then we get ln of v, which is equal to ln of t minus 2. And then I don't know, I guess we do the plus c outside of the ln, I think. So, I don't know. Let me actually ask. I'm just curious. So when we integrate dv over v, um, do we put, well, okay, wait. Let's say, let's just derive everything, because deriving everything is the nice. So let's say we have ln of a plus b is equal to c. That means that e to the c is equal to a plus b, right? Right. Whoa. Okay, I'll be right back. I take a shit. All right. Okay, okay. Okay. Good. So, okay, so we're gonna get y squared over 2 minus y is equal to ln t minus 2 plus c. Okay. So I'm pretty sure that I found a formula, which is y squared over 2 minus y is equal to ln of t minus 2 plus c. Now, the problem that I'm so now, okay, so t must be greater than 2. That's for sure. Wait. Wait, y of 0 equals 0. Dude, what the fuck? Oh. Dude, the fucking the plus and minus and the absolute values are actually killing me right now. Wait, is 1 plus y? Oh, God. Dude, I am so fucking cooked. Oh, seriously? You gotta complete the square to solve this thing? No, god damn it. Dude, these problems are tough. What the hell? I like that this just stopped working. Okay. Dude, I'm so fucked. This is like... Okay, y plus 2 squared. I mean, when the completing the square came out, I was like, oh, God. All right. Dude, these integrals are actually destroying me. God damn it. What the fuck? Okay, man. I am so sick of getting absolutely cooked by these integrals. It's really brutal. I mean, I just keep getting them wrong. I mean, I just wish the actual section of the book went over how to do some of these problems. Okay, last one of these. I mean, I was like, oh man, I can't wait to get through these because these are so hard. And then these ones are hella hard too. These ones were hard because I didn't understand. You needed to find the functions using language like that. And I just got completely confused by the absolute values and the plus and minus. I need to redo 10, 11, 12. I need to redo all of these when I'm like, I don't know. All right, 16. Come on. I'm not going to fuck this one up. dy dt is equal to t over y minus 2. Okay? Pretty simple. So I'm going to multiply y minus 2 for both sides. I'm going to get y minus 2 times dy is equal to t dt. All right, so this one's like the easy case. I mean, this usually I like integrals like this. All right. Dude, there's just no way this lawnmower is still going on. This guy has been not lawnmower, leaf blowing for like an hour and a half next door. Oh my god. It's just Nat Friedman was right. We need like robots that like quietly pick up the leaves. Like do not just have constant noise pollution. It's just so bad. Plus it kicks up dust. I'm sure it's bad for so many reasons. All right. So we're going to integrate, okay? We should get y squared minus 2y. Y squared over 2 minus 2y is equal to t squared over 2 plus c. I'm pretty sure what you're supposed to do, actually, is you're supposed to maybe do y minus 2 squared over 2. And you keep the squareness of the whole thing. Is equal to t squared over 2 plus c. You multiply by 2, then you get y minus 2 squared is equal to t squared plus c. Then you square root, so you get y minus 2 is equal to the square root of t squared, which is t, but I guess it's plus or minus t plus c. And then plus 2. So you get y of t is equal to plus or minus t plus 2 plus c. And we have y of minus. Dude, I actually can't believe this. I just can't believe it though. Oh wait, when was that message at? Oh, I'm coming back. Hold on. All right, hold on. I'm coming. I'm gonna end the stream. I got absolutely demolished. Okay, this one. Okay, 17 I can actually understand. I'm done. I'm done, dude. This fucking lawnmower absolutely destroyed.